having a sense of whether an operation will converge on a particular answer going in would be the basis of something like that, right? So, but I'm getting ahead of myself. We'll talk about that a little bit more later. Convergence, divergence of a series. Well, we have the basic ones, the arithmetic, which is rare to the point where we're not actually going to work with it too much, because the only way that an arithmetic series will converge on a particular number is if it's the sum of 0. All right, so basically all coefficients have to be equal to 0, because otherwise it's never going to converge. It's always going to either be increasing or decreasing. All right, geometric series, that's the exponential situation. It's either increasing or decreasing in an exponential fashion. All right, those tend to converge, but only under the right circumstances. All right, and there's some other rules here that sum and difference rules and constant rules, but that's pretty consistent with everything else.
When you say situation like what concentrations do increase?
That would be the subject of the next page, the page after that, and the page after that. So we're getting there. So convergence and divergence of a series. What does it mean for a series to converge? Well, I mean, we've kind of discussed this already. We settle on a particular value. And again, not as important what the particular value is. All right, so it's asking us here to find the first 10 terms of the sequence of partial sums and list them below. All right, partial sums, that's kind of weird, because when you look at it, you say, well, isn't that what's written up there? I have, looks like 10 things, maybe not, I don't know. But, and it involves sums, but what is this partial component? It seems like we're using overly complicated verbiage. What it's telling us to do is add the first value to itself, I mean, not to itself, but just collect the first value only, then add the first two values, then the first three values. So it's really a cumulative sum. All right. So basically what it's asking us to do here, and we would continue on from there, hoping to find a pattern, and we'll get the calculator involved in a second here. But what it's basically telling us to do is really to find the sum from n equals 1 to 1, n equals 1 to 2, 1 to 3, 1 to 4, 1 to 5, and so on. All right? Not just a listing of the sequence. So let's, like I said, get the calculator involved. All right, this I don't need. I don't know why it ever comes up. And again, somebody. So you can do it as a simple sum. So 3/2 plus 3/4. I already had the 3/2. And then math bracket. Because, why not? So my first entry is 3/2. Then what did I say, 9/4? Well, the next one would be 12/4, right? Because I'm just adding 3/4 to it. Oh no, I'm adding 3/8, so it's more than that. (21/8). I mean, really, I'll just kind of steal my own thunder, tell the punchline of my own joke, whatever. But basically, all of this is to demonstrate to you the idea that this idea of finding an infinite sum is not as easy as one might think. All right. We do want to get technology involved where possible, but only if it has meaning to do so. All right, so my fourth entry. So I'm adding 3/16 to that. So 45/16. All right, so each one of these entries is the most accurate sum that we can come up with from this sequence, right? Because the more terms that we incorporate, the more accurate our cumulative sum becomes. All right, so the next one, just to use the entries that I've already used, I'm really just taking my previous answer and adding to it. So I have 45/16 plus 3/32. So it's 93/32. Is that 93? Yeah, 93. Oh, I was hoping it would be something nice, like 96/32. Whatever, I'll just keep doing it on the calculator. So plus 3/32. Meh. Math. Meh. Meh. So, yeah, it doesn't even reduce. All right, so add the next value. So now I'll just do it exclusively on the calculator. 3/64. So top number in my sequence is staying the same. Bottom number is getting smaller and smaller. So maybe that has a role to play in this. Math, enter. 189/64. Four more to go. 3/128 is next. And just so you know, the benefit of doing it out this one time is so that we can learn why we never want to do it out. All right. But you do tend to get an understanding of where the numbers are coming from a little bit better. 765/256. Now, it does seem like maybe the top is outpacing the bottom. Now, will it go to infinity? I don't know. It's not outpacing it at such a wide margin where you're like, wow, it's definitely going to get to infinity. You know, it's in decimal form. I mean, before I put it in fraction form, it seems to be closing in on a particular number. I mean, if you don't see it right away, maybe in the next calculation you'll see it. Because I'm hitting math frac, but right before math frac, there's a nice decimal there that kind of gives you a sense of where these numbers are going. It's just I'd rather write the fraction down. 1533/512. And you really don't even need the calculator for the denominators anymore because you're noticing consistency there. It's all the same as the originals. All right, but those decimals do seem to be closing in on something. 2, 3, 4, 5, 6, 7, 8, 9, one more. So then 1024, 3/1024. Oh, yep, there we go. Moth, enter. So 3069/1024. Exactly as I predicted. I mean, not the fraction. The decimal, though, you look at that decimal, you're like, okay, I get it. I see where it's going. 2.997. Before that was 2.994. 2.99 something. The first one, I think, yeah, the first one was 1.5. 2.25. It started climbing, but eventually it started to level off at a particular number. Right? That number appears to be 3. If I had to call it at this point, I'd say, okay, it's converging to the number 3. So the question would be, well, how do I get that without doing all that? I don't know if there's 2 ways to do it. Well, 3 ways. One is still visual. But if you want the calculator to do the work, you know this sum sequence business here? I don't know that you need to do any of this in order to get it. We can look at that later, but in terms of just getting a quick hit, alpha window, there's one that says summation. It's a pretty good option. You can choose whatever variable you want. I like I. There is no infinity button. So what you do is you just put in some really, really large value for your top number. I'll put in 1,000. I don't know if that's large. Contextually, it may not be large. But I like to believe that that's a sufficiently large number. If it's not, I'll do it again. I'll make it bigger. So 3 divided by, actually, let me just try something. Oh, it does work as a fraction. Okay. Three over 2 to the I. You could use n. Doesn't matter. I grew up on I, so. And then like 45 and a half minutes later, I went too big. Go big or go home. I guess I'm going home. Okay, so maybe
Get that, fraction.
alpha window. I'm sorry, alpha y equals.
Oh.
Alpha window is the other thing. Alpha y equals. All right, I'll try 100. Less ambitious. It's thinking. Oh, you don't get the payoff I got. All right, hold on. There it is. It's a 3. All right, so, I mean, the calculator doesn't know analytically, algebraically, calculus, how it's 3. It just knows that the decimal that it got was so infinitesimally different from 3 that it wasn't ready to make the call that it's something other than 3. All right, so you can get it that way. There's definitely some issues that arise because any kind of problem that has any sort of domain consideration, you start getting into inverse trig functions, log functions, things like that, it might get a little hairy, you know, because you might think it's closing in on 3 because it looks like it is, when in reality it's closing in on E, 2.718 roughly. But it looks like it's going to 3 because you expect it to be a whole number value, but really it's going to some other number. And it's not as obvious just by looking at a table or something like that. All right, so the formula for the infinite geometric series. All right, well, the infinite geometric series, so let's start with that for a second. Sum from n equals 1 to infinity. And it's right here, if you're wondering. Oh, well, there's 2 variations of it, but this is the one that we want. Actually, it really doesn't matter. Because there's a 3rd variation that works equally the same. You'll just have a different a sub 1 value, but it's r for the n. This one also works, but this is really, even my refined notes, they still have room for typo bonus. Somebody can claim that. Anyway, so n equals 1 to infinity, a sub 1 r to the nth. Anything that follows that model is going to be considered a geometric series. We talked about it last class and how it's kind of weird to think of it as geometric when it looks exponential, but we know that geometric figures, as you increase dimensions, their metrics, whether it's area, volume, whatever, increases exponentially. Right? So that's the connection there. It's a weird connection, but that's actually the correct connection. All right, so I have 3 over 2 to the nth. That doesn't look like what I just wrote down precisely. But it looks a little bit closer to that if I write it as 3 times 2 to the negative nth. Slightly better. I need a positive n. All right? So that would be the same as if I were to write it as 3 times 2 to the negative first to the n. Which would be the same as saying 3 times 1/2 to the n. That actually follows the model. All right, so from this, we can identify an a sub 1 and an r value. Houston, we have a problem. No, I don't think I have a choice. Yeah, that other form is actually the one I wrote in. It is a model of a geometric series, but it doesn't correspond with this formula. Yeah, so the first entry, okay, so it's weird, but this formula corresponds to this rule. Because this is going to give me a 6 in a second, and that's not what the sum converges upon. Yeah, the first entry is 3 over 2. Yeah, we have to get it in the right... I'm just debating which formula to go with because I don't like working with the 0 on the bottom. I only like working with the 1. And this was the best of both worlds. I could modify the formula actually. But then it would have to be a sub 2. Oh, I got it. Okay. Yeah, that's what I'll do. I'll just invent a new formula. Very slight modification. Because with this model comes great responsibility. Yeah, with that model, your a sub 1 would be insufficient. All right, so new typo for somebody. Because I didn't want to undo what I just did. So a sub 1 would be 3. The r value is 1/2 in red over 1 minus 1/2. So 3/2 over 1/2 will be 3. Okay, good. This one out? Yeah, it came from here, so when we have 2 to the negative first power, it's a little reciprocal action. I'm sure this is a rule written by somebody somewhere. And the quirky thing about these sequences and series, specifically the series, is that we ideally want them to have an index at the bottom that starts at 1. But some of them are better served if they start at 0 because they connect better with a particular function model. And so there is sometimes a case where we have to make some maneuverings, right? It's just this we can manufacture from what we have here. We'd have to manipulate this a little bit. Basically, just divide by another 2 and make it happen, but it's not really working. You'd have to write it as 6 times 2 to the n minus 1, I think. And I think that was probably a more confusing fix than just changing the formula. All right, but anyway, we haven't done any parametrics in this class yet, right? Does the word sound familiar? Parametric equations, parametrics? No? Okay. All right, so this is a nice way to get a visual representation of what a sequence would look like, or a series would look like over time. All right, time being kind of what you think of it. So number of steps within a sequence or the series, or it could actually represent time. So you'll see that in Calc 3 if that's where you're going. So in an ordinary window, we have x min, x max, y min, y max, things like that. But what we're going to do is change our mode to be in parametric form. So not function mode, but parametric mode. Then when you hit y equals, you see instead of just y1, y2, y3, you see x1, y1 of t. x2, y1 of t, x2, y2 of t. But I think more importantly, when you go into your window, you see t min, t max, and t step. You see x min, x max, y min, y max like you have everywhere else. But specifically, T min and T max, and also very important, the T step. We'll adjust that in a second. But what we're going to do in our y equals menu or window, in xt1, we're just going to put in a t. All right. So that t value is going to go by integers. So I'm going to hit. You see this xt theta n key that not everybody actually uses to get an X on their screen. A lot of people, more people than I would have thought, use alpha store. This key, depending on the mode that you're in, will give you a different variable. Function mode, it gives you an X. Parametric mode, which if this is the first time you're in parametric mode, this is the first time you're going to experience it, it'll give you a T. When you're in polar mode, it'll give you a theta. And when you're in sequential mode, it'll give you an N. All right, so I'm going to hit this button. T comes up. And I hit enter. All right. In the second part of the parametric, so x equation in terms of t, y equation in terms of t, I'm going to put some sequence. All right. That's the same as alpha window option 2. All right. So I'll write it in here first, and then I'll put it on the smart notebook. So you're going to go from t equals 1 to t. And then you're going to put your function in. All right, so it's 3 over 2 to the t power. All right, so again, this is the same. And you could revise your notes because I think, when I wrote this, people had TI-83s mostly. Now it's TI-84s for the most part. So it's the summation t equals 1 to t. So we're not capping off our t values. And then 3 divided by 2 to the t power. So this. Basically, it was in a different form. It's really still like this. I'm leaving my upper bound uncapped. So, it's not the same as putting in an infinity, but it's the closest we can do to getting that. All right. The window settings, hugely important. You're not going to get much meaning out of this unless you have the appropriate settings. The good news is, for the most part, you can leave these settings as is. So, window settings for T, 1 to 20. Because honestly, if you're doing this out by hand, whether you're scratching it out on paper like we did above, or if you're using technology, If you can't get a sense of where it's going, if it's converging on a particular number after 20 calculations, then you're probably not going to get a sense of it, right? And that can happen for one of two reasons. One, because there is no number to get a sense of because it diverges. The other would be because it's converging onto a number that's not familiar to you. All right, that's the case where you're closing in on, I don't know, 25.372. And you're like, okay, what is that? And it turns out it's some multiple of pi that you're just not familiar with. All right, t step, I'm putting in a 1. X min, negative 1 to 20, even though you don't really need the negatives. I do it so that you can actually see the axes. You know, you get a good look at it. Figure if you go up and down 20 units, up 20 units, right 20 units, that's good enough. But that, if you're going to manipulate anything in this window, that's what you're going to manipulate, your X information. And the reason why is because that's going to be particular to your function. This is an exponential function. Exponential functions typically live in the first quadrant. Right? Whether they're increasing or decreasing, that's just pretty much how they exist. Right? If you have something that's like a cubic function or something like that, well, first off, it's not going to converge. But second of all, so you shouldn't need to look at the graph anyway. But second of all, you know, like when you're looking at the graph, you may have to make some adjustments, but you'll see. You hit graph and you see nothing on your screen, you know you messed something up. So hit graph, and we don't see nothing on our screen, so that's pretty good. It's nice. It's always good when that happens. Couple of little modifications that you can make. You can I'm perfectly fine with it in this curved appearance. There's nothing wrong with that. Some people like to put it in dot mode, right? So if you go to mode, there's an option. You got thick, thin, dot thin. My vision is shot. I mean, I can barely see that curve that was on there, and it was set at thick. So if I'm going to put it in dot mode, I'll put it in dot thick. And it'll plot just the points and not connect them. All right. The reason why that would be beneficial is because we're talking about a sequence that becomes a series, but the sequence of partial sums becomes a series and eventually an infinite sum. They're discrete pieces of data. It's not a connected dot situation, right? Unless you can tell me where the 1.279th value would be, I don't feel like I would need to see that on the graph. However, if you put it there, you're not losing credit because I'm not even going to see the graph anyway. So if I had trace, though, that's the cool part. I can scroll, and I can actually see the movement of the y values as I increase my, well, t value here, but that corresponds to n. So now it's pretty clear that that puppy is converging in on 3. All right. Can you use this technique for any kind of function? No. Because sometimes it looks like it's diverging on your screen. It doesn't look like it's settling into a particular number, but it is, just you're not looking at the right part of it. So you could run into issues. Yeah, up to 2. So that's what it looks like. Oh, in mismatch, you have one of your plots on. So go to whatever plot's on and hit enter.
I don't have it on.
And it's pulling your data.
Well, that's why I had it originally, but I know I could do it like the sequence.
Oh, this is the sum sequence. The summation symbol, so you don't actually need the symbol. All right, so it's a technique. I mean, it's a good place to start because if you put your the argument of your summation, the body of your summation in as your y1, and take a look at the picture. If it's converging on something and it's obvious, then you already know the answer. You don't have to show me anything beyond that. I mean, you could bet there will be plenty of situations where it's not going to be as cut and dry, but take advantage of the situations when they are, So like this one, for example, 3 over 2 to the nth. All right, slight modification. Parentheses around the 3 over 2 before you raise it to the end. All right. Now, I would say, the first 5 terms of the partial sum, calculate it out like we did here, but I think you get the point on that. I'll hit graph. That looks like it's getting out of control pretty quick. Those points don't look like they're settling in on a particular number. It looks like it's going to infinity. All right, so I would be confident in saying that we're diverging here. All right, so if that's the case, all right, so we're going to assume that we're diverging. Let's get some partial sums. Graph is going to infinity. But a little justification. I can do the trace thing, start writing down values. I can go into my table. The thing about the table, though, is, just your T settings are important. Knowing how to work within your table set, that's important. So you see something like this. This was great. This is beautiful settings for the last time I did a problem that required these settings. Not so good right now. So to change it, second window, table start. I want to start at, what do I want? 1. What do I want it to go by? I want it to go by 1s. Then I go into my table. Then I have what I need. All right, I only need the first 5 entries. But I have a whole lot more than that, and just because the question's not asking you to go beyond the first 5 terms doesn't mean that you have to ignore them. Like, I think it's going to 19.781. Why? Because he said only to look at the first 5 terms. No, that's all I want you to list. But it's pretty clear, if you look down further, that it's going way beyond 19.781. It's getting larger and larger pretty fast. Right? And if you scroll down this list as far as you want, it's never going to settle in on a particular y value. That's our justification, at least visually, for why it's diverging. All right. Now, in terms of the formula, the new and improved formula, a sub 1 r over 1 minus r. In this model, which is pretty close to what we need, we can assume coefficient of 1, so the a value would be 1, the r value would be 3/2, and then on the bottom we'd have 1 minus 3/2. So 3/2 over negative 1/2, which would be negative 3. Okay, because again, whatever your leading coefficient is, that's a sub 1. This is my r. All right, well, how do I know that negative 3 is telling me that it's diverging instead of actually telling me that it's converging on negative 3? Yeah, exactly. Slash common sense, basically, because you got a negative sum from only positive numbers. How could that have happened? Doesn't seem to make sense. Now, just because you're working with n values that are positive doesn't mean you can't get negative numbers as a result. but the result of each one of these calculations is a positive result. Each element of the sequence is positive. So then, how on earth would I get a negative number if I was adding up positive numbers only? It's not possible. All right. So that's at least reinforcing that it's divergent. And that was page 74.